find your 7-3 notes, and we're going to do 2 of the problems on the back side. Tell me why those triangles are similar. Hannah. Okay, so angle A matches with what? Angle D. So you could do the same thing with the angles over there as well. Okay, but the triangles are then similar by what method? Angle, angle. Give me the similarity statement. Yes. Good. So you have to pay attention because this one, it's not just a simple reflection. A and E do not match up. A and D match up. Okay, and then let's match up corresponding sides here. So what's the scale factor of the two triangles, between the two triangles? What's the scale factor? Liam? Okay, and I would kind of go left to right and call it 1 to 2, but yeah. The scale factor, you're comparing a 30 to a 60. So our proportion, we could say 30 is to 60, and then just kind of reduce that as 1/2. What's the other part of the proportion? Nick? X over 38.6. Now, X is across from the double marked angle, and 38.6 is across from the double marked angle, right? So it'll be X over 38.6. So X should be what? If you can cross multiply, you can just kind of like think about it. Are you dividing by 2 or multiplying by 2 on 38.6? You're dividing by 2, 19.3. Okay, and we're using that parallel lines cut by transversal make alternate interior angles congruent. The triangles are similar by angle similarity. Okay, how about the next one? Kylie, tell me what you can get from parallel. Yeah. I know what you mean by R, but what's the correct name for that angle? Yeah, so remember when it's got more than one angle, that vertex, you need to name it that way. Okay, so we're using parallel lines cut by transversal. What did you say those angles are? What kind of angles? Congruent corresponding angles. Okay, now, when you go to set up the proportion, tell me what that's going to be. What is the scale factor? Oh, here we go again. Sorry. Finley, what's the scale factor? How do you know? So be careful. It's not 3 to 10. It's not 30 to 10. It's 30 to 40, right? If you need to think of these triangles pulled apart, if you find that helpful, then just, redraw them. I'm being sloppy, but it's okay. 30, 30, 32, 40. And how long is the side down here? Jackson? 32 plus X. So then we could do 30 to 40 equals 32 over 32 plus X. Or if I did 30 over 32, what would be the other side of that proportion? Charlie? 40 over 32 plus X. Now they should give you the same thing. Again, they're equivalent because 30 times 32 plus X equals 40 times 32. Okay, those are equivalent proportions. They should give you the same answer. I want to do it this way for 2 reasons. Number one, it's easy to simplify 30 over 40 and just call that 3/4, right? And I also want to talk about this. Are you allowed to divide the 32s? Is it okay to divide 32 on the right side? Yes? Yes? Jackson's saying no. You have an idea of why you're saying no, Jackson? You're saying yes? Yes, okay. Remember when we were doing the problems? I'm having this issue with my cord. Well, really, it's probably with my iPad. Yeah, and it just every time my cord gets a little wiggled, it's causing an issue. Okay, remember when we were doing like the problems where you had like 3 plus 6 plus or minus 6 root 2 over 12 or something? And I told you you have to, if you take something out of 12, it's got to come out of those numbers as well. Same thing applies here. When you have that plus sign, the only way you can divide something out of 32 and 32 is if you take it out of here as well. And obviously there's not a 32 there. So you're not going to be able to just cancel out the 32 there. So be careful. There's lots of algebra pitfalls that happen on these problems. So just watch out for those things. Okay. And then I know you know how to cross multiply and solve. I'm not going to do that because I don't want to take the time to do that. Okay, let's go over homework. Homework, chapter 7, number 18. Now, you're going to notice two problems that I want to talk about. So first of all, make sure on a problem like number 2 that you are not assuming that those lines are parallel. We don't know if these are parallel lines. Therefore, we don't know if these angles are congruent. So you actually don't have enough information for problem number 2. Okay, problem number 2, you'd either need to have the other pair of angles or else you'd have to have, and I didn't say this, but you could have also, if they gave you these segment lengths or like that one and that one, then you could do side, side, side or side angle side. But as it's given, you don't have enough information to determine similarity. And then number 4, be careful with number 4 because it's like the one we just did. 16 is to 24. 6x plus 2 is to 7x plus 7. Nick? No. Yeah, that'd be fine. That's fine. Yeah. Questions on 1 through 4? I'm going to go kind of fast, so if you need to take pictures, go ahead and do that. How about these? Oh, I just realized, I'm sorry, I was on page 2, wasn't I? Sorry about that. Okay, we'll go back up in a minute. Again, on number 5, when you compare 6 to 8, you're using sides of the similar triangles. Then you need to compare x plus 7, and then the whole side of the big triangle is 2x plus 6. Now, you could also do x plus 7 is to 6 as 2x plus 6 is to 8, for example. If you find it easier to use two sides of one triangle for your left side than the same corresponding sides the other triangle on the other side, that's fine. Now, for the one down here, just a few notes. 5 feet 3 inches is 63 inches. It's also 5 feet and a quarter. Okay, why is it not 5.3? Why is 5 feet 3 inches not 5.3? Okay. Yeah, you're taking out of 12 instead of what? If it was 5.3, you would have been taking out of 10, right? So 5 feet 3 inches, that's a quarter of a foot. So that's 0.25. If you decide you want to put it into inches, that's okay. It didn't say you had It's kind of weird to give a lighthouse height in terms of that many inches, but it didn't say it had to be in feet. So you could technically leave it in inches or convert it back into 84 feet. Okay, but there is no rounding going on here. If you use 5.3, you might have gotten something close, but it may not be exactly right because you probably had to round. Okay, here's the picture that would go with that. So your proportion needs to be something like that over that equals this over this, or 128 over 8 is x over whatever you use for that one. Okay. Any other questions on page 2? Do you want me to? Here, hold on, Yusha. There you go. Okay, on the first page. How do you know on problem number 1 that these sides are proportional? So you could use setting aside. They didn't give you actual numbers there. How do you know if the sides are proportional? Caroline? Right. Exactly. Good. Well said. So I'm just going to make up numbers. Let's say this was like 2 and that was 7. Well, this would also be 2 and 7. So it's the same ratio, right? Or it is easier probably to think the first thing Caroline said was that's a 1-to-1 ratio. So is that. So yeah, they're proportional. Okay, so even though they didn't give you numbers there, sometimes it's more difficult to kind of see it when they don't give you numbers, they just give you markings. But that would be setting aside. On this one, you don't really have enough to be able to tell exactly what the relationship is supposed to be, the matching is supposed to be, so either way would work. Questions on 1 through 4? Yes. Yeah. Yeah, because they have to 180, this one has to be 30. That one's going to have to be 60, and then you got an angle. Yep. And that's a little tricky too. Like it's like, yeah, of course you can find those third angles, but if you aren't paying attention, you might be thinking, oh, I don't have 2 of the same angles. So yeah, just be careful about that. Okay, here's the last 4. All of those you can prove similar by angle. Oof, sorry. Now again, this kind on number 7, when you compare 6 to 12, that's a 1-to-2 ratio, but you need to be comparing x plus 5 to the whole entire side. Okay, you could also use something like x plus 5 over 6 equals x plus 14 over 12. But you need to make sure you're using x plus 14 and not just 9. 9 is not a side of a triangle. So you got to have x plus 14 in there. And same idea with number 8. Now, number 8, you have to find x, and you also have to answer VT. So if you had 3.4 or 17/5 as your answer, you just forgot to add 2 because it actually asked you for the length of that segment, not just what x is equal to. Questions on anything on those 4? The whole idea, the main idea of this lesson has to do with this picture right here. What we're looking at is a right triangle. ABC is a right triangle. if you can't see that right angle very, very well. That at angle C on the big triangle, that's a right angle. Okay, we're dropping a segment that makes a right angle with the opposite side and goes through a vertex. What's that called? When you go from a vertex and make a right angle with the opposite side, what is that? Okay. An altitude. Okay, so we have a big right triangle. We've dropped an altitude to the hypotenuse. Okay, and then it creates this picture, and there's three triangles there. Right? There's this one, there's that one, and then there's the big triangle. I'm going to call this baby triangle, mama triangle, and papa triangle. Okay, something that's related to that diagram is something called the geometric mean. So you know what the arithmetic mean is. The arithmetic mean is where you add two numbers, divide by 2. We're doing what's called the geometric mean. So there's kind of two ways to think about geometric mean. One way is to look at this proportion. The number that goes in opposite corners in the mean positions, the number that goes, it's the same number. One number that goes in opposite corners of that proportion means it is a geometric mean between the other two numbers that are in the other corners. If you cross multiply that, what do you get? Sammy? Oh, you're killing me. It would be x squared. Yeah, x squared equals a times b. And then if you solve that for x, you would get what? Liam? Square root of ab. Now, technically, you would get plus or minus square root of ab. But when we're doing geometric mean, our answer is always going to be positive. Okay, so there's two ways to think about geometric mean. One way is to think of it like a proportion. The other way is to think of it kind of like a little formula like that. And they mean the same thing. They're just kind of in different ways. So it says the geometric mean between two numbers is the positive square root of their product. Now, you know product means multiplying together. Take the square root of the answer, and then you're giving me the positive value, not the negative square root. So as far as numbers go, let's say I have a proportion and I put the number 6 here and here. Tell me two numbers that I could fill in to the corners there that would make that a true proportion. Give me numbers that I could fill in to make a true proportion. There's tons of different ranges you can give me. Give me an example of two numbers that would fill that in to make a true proportion. Liam? 2 and 3, is that what you said? 2 and 8. Is that what you said? Okay. What is 2 over 6? What's 6 over 8? Are those the same fraction? Okay. Another reason that I know that that's not correct is because 2 times 8 is what? But that's 36, right? So let's fix one of them. Can you tell me what that should be if it's going to reduce down to 1/3? What does this number need to be? Let's make it simpler. Let's say that this is 3 over 6, which is 1/2. What does that number need to be? 12, right? So that's an example of geometric mean. 6 is a geometric mean between 3 and 12, because 3 times 12 is 36, and the square root of that is 6. So a geometric mean is a number that fills in that proportion where they're in opposite corners like that. Okay, and again, two different ways you can think of it. Now, if I want the geometric mean between 4 and 25, two ways you can set that up. You can either say, okay, I'm going to make a proportion. I don't know what the geometric mean is, but I know it's going to go in opposite corners like that. And I'm going to fill in the other numbers I know, 4 and 25. When you cross multiply that, Charlie, what will that be when you cross multiply? So x is what? And again, if this was just an algebra problem, you'd say plus or minus 10, but because geometric mean is always positive, you could use the positive answer. And again, another way of thinking of that is you can say, okay, the geometric mean is the square root of the product of the two numbers. So you can do 4 times 25 and then take the square root of that, which is 10. It should give you the same answer both ways. When I'm doing triangles, I think of proportions. When I'm doing geometric mean with two numbers, it's probably simpler to do the little formula kind of way. But both of those should make sense to you. Okay, so again, arithmetic mean means add and divide by 2. Geometric mean means multiply and square root. Nick? You can do either way. It's fine. As long as you can show me one of those calculations, that's fine. Okay, and then for the second one, proportion way would be x goes in the opposite corners in the mean spots. 3 and 24 would go in the other corners. Okay, what is that when you cross multiply? X squared equals 72. How does that break down? Emma. There's a bigger one. Square root of 8 breaks down again. So we can do that. Square root of 9, square root of 8 would be 3 root 8, but 8 has to break down again. Okay, times 3 would be. So the reason it's 6 root 2 is because 36 actually goes into 72. So you can do it in steps like that. If you don't see that at first, then you can always do it in multiple steps. But 36 is actually the biggest perfect square that goes into 72, so it's 6 root 2. And again, the other way, probably easier, square root of 3 times 24 would give you the same thing, square root of 72, 6 root 2. It'll give you the same answer no matter which way you do it, but I want you to kind of understand how they are the same. You could do it either way, and it should still make sense. Okay, here's our triangle. We got a right triangle with an altitude drawn to the hypotenuse. I want to talk about the relationship between this triangle and the original big triangle, the ABC triangle. Why would, that's Mama triangle, why would Mama triangle be similar to Papa triangle, which is the original big triangle? Why are they similar? Why are Mama triangle and Papa triangle similar? Lachlan, what do you think? Talk a little louder. When you say they share two of the same sides, they shared this side. This is not actually a shared side because that's only part of this side, right? Okay, that's not a side of the big triangle though. Nick, what were you gonna say? Okay, they both have right angles. So I need something else though for similarity. You gotta have at least 2 angles or else all the sides or else 2 sides and include angle. Do we know any other angles? Hannah? Awesome. Okay, so the triangles are similar at angle because they actually have physically the same angle at B, and then they both have right angles. Okay, that's Mama triangle and Papa triangle. Okay, how about on the other side? What if I compare Papa triangle and baby triangle? Why are they going to be similar? Why are they similar? They both have right angles and thank you. They share angle A, right? Same idea as on the other side, but they share angle A and then they also should have both have right angles. Okay, so that theorem is going to say the two triangles are similar to the original triangle and they're also similar to each other. So all the triangles are similar by angle. And you've got a right angle and a shared angle. Now, technically, baby triangle is similar to Papa triangle and Mama triangle is similar to Papa triangle. And then Mama and baby are similar because they're both similar to Papa. So it's like a transitive kind of thing. So triangle 1 is similar to triangle 2, and triangle 3 is similar to triangle 2. Therefore, these two are similar to each other. Okay, but when you drop an altitude in the right triangle, you create two triangles that are similar to each other and to the original triangle. Okay, I'm going to take that picture and pull it apart, because when we're thinking about similarities, sometimes it's easier to see it if we have it kind of oriented all the same way. So I literally took that triangle and I copied it down here. Okay, so this is just a copy of the triangle that's directly above it. That's triangle ABC. So this is Papa Triangle. Notice that I'm reorienting them so that the right angle is at the top and the bottom would be the hypotenuse. Here's Mama Triangle. I need to figure out where, what those vertices should be. How do you know where to put the vertices? Well, which one in Mama Triangle, which one's the right angle? Which vertex is the right angle in Mama Triangle? Charlie? D. Okay, and then how will I know? So Mama Triangle has D, B, and C as its sides. How will I know where to put B and where to put C? Well, there's angle B, right? Here's angle B. Where should B go in this picture? Nick? The bottom what? It needs to be in the same spot, right? So it should go over here. It wouldn't rotate, it would actually flip, like flip like off the page in 3D way, like it flip towards you or away from you or whatever. Okay, because the altitude side, oops, sorry, the altitude side right here is actually right there. And the hypotenuse came down here. So it's like you flipped it over. So B stayed where it was. We just kind of like took it and flipped it over. And that means that our last vertex there is C. This is Mama Triangle. Okay, in Baby Triangle, the right angle is where? In Baby Triangle, where's the right angle? Finley, where's the right angle? Yeah, angle D in Baby Triangle is the right angle, so that means D has to go up here. Okay, and then your A and C, you got to figure out where to put them. So where should A go? So here's angle A. That means it's down here in Papa Triangle. Where should A go in Baby Triangle? Bottom left. Okay, so remember we had those shared angles. Hannah told me, oh, they're similar by angle because they share that angle. That's how it's got to work when you reorient them as well. And then your last vertex there will be C. Baby Triangle. Okay, let's write a similarity statement. Now, when I write a similarity statement, I'm going to do it a specific way. You don't have to do it this way, but remember, however you write the first one is how you got to write the second and third. I'm going to start at the right angle, go along the short leg, and then along the hypotenuse. So that's from the right angle along the short leg, then along the hypotenuse. Now, in these pictures, we've got the hypotenuse is always across in the right angle. You have a short leg and a long leg. Now, when I'm saying long leg, I don't mean it's the longest side in the diagram. I mean it's the longest of the two that are not the hypotenuse. All of these have been reoriented, so the hypotenuse is at the bottom, the short leg's on the left, long leg's on the right. Okay, hypotenuse at the bottom, short leg on the left, long leg on the right. When I write the similarity statement, I'm going to go from the right angle along the short leg along the hypotenuse. And that's because I don't want to have to redraw these pictures every time. I want to be able to look up here and figure out the similarity statement. Okay, so if I start at the right angle, that's C, and then along the short leg is to A, and then along the hypotenuse is B. Do the same thing for mama triangle. What would be the correct order for mama triangle? Nick? DCB. Again, starting at the right angle, along the short leg, along the hypotenuse. DCB. Nyla, what's the correct order for the baby triangle? I'm going short leg, hypotenuse. So here, start at the right angle and go. They need to all look the same. DAC. Now, the thing is that if I look at it on here, I can do the same thing without having to have redrawn them. So here's my right angles. Okay, if on Papa Triangle, I go from the right angle along the short leg along the hypotenuse. Then on Mama Triangle, I can go from the right angle along the short leg along the hypotenuse, DCB. Right, that's what we've got there, DCB. And then in Baby Triangle, I can go from the right angle down here along the short, down here along the short leg along the hypotenuse, DAC. And I can get that similarity without having to pull those triangles apart and redraw them and all that. So I always go start the right angle, go along the short leg, go along the hypotenuse, because those are easy things to recognize. The right angle is an easy place to see. Okay, and then you can tell short versus long most of the time. Complete the proportions. Now, these proportions are true because we're comparing similar triangles. AC and AB. Which triangle has both AC and AB as two of its sides? AC and AB. Which triangle has AC and AB? Liam? Okay, Papa Triangle. And in Papa Triangle, AC is which side? Is that short, long, or hypotenuse? AC? That's the short. And then what about AB? That's the hypotenuse. Okay, that means if you're comparing short to hypotenuse in Papa Triangle, then your proportion must be comparing short to hypotenuse in another one of the triangles. So if they gave you CB, which triangle has CB as its hypotenuse? George? Mama Triangle. That means this proportion is comparing Mama Triangle and Papa Triangle. Okay, we're going short to hypotenuse. Now, do pay attention to the order, right? So if it says A to C for Papa and then A to B for Papa, then it should be what over CB? What needs to go in that blank right there? Emma, what should go in that blank? This one. So it goes AC to AB, so it'll be what? CD. Okay, order matters on these because of the fact you're using similarity. That'll be CD. Short to hypotenuse, Papa and Mama. Okay, for the second one, which triangles are we comparing? Okay, so AC and DC. Which triangle has AC and DC as two of its sides? Let me get rid of the highlighting here. Which triangle has AC and DC? Isha, which triangle has AC and DC? Okay, so that's baby. Is AC short, long, or hypotenuse? And then what about DC? In this one, AC is hypotenuse. What's DC? It's what? Yeah, it's a long one. Okay, I just didn't hear you. Hypotenuse compared to long. So that means in the other triangle, we also got to be comparing hypotenuse to long. Now, if they gave you AB, which triangle has AB as its hypotenuse? Kylie, which triangle has AB as its hypotenuse? That means we're comparing baby triangle and Papa Triangle. So baby triangle, we're going A to C and then D to C. So in Papa Triangle, we should be going AB to what? Sally, what should be on the top? I'm sorry, on the bottom. CB. Now, you know how I said I didn't want to have to redraw these triangles every time? I just kind of did that to help you sort of see what's going on. If we have the similarity statement, we can get this a little bit easier without having to like look at the pictures every time. So which of the triangles has DC and AD in it? DC and AD. Which triangle should I be looking at? Let's go 1, 2, or 3. 1, 2, or 3. Which triangle has DC and AD? Mariana? Okay, so if we go from D to C in the numerator, and then from A to D in the denominator, I'm going to do the same pattern on another one. Now it says DB. So which triangle, if I went DC on this one, I went DC, and I do the same pattern on the other one, which triangle should I be looking at? First or second? Nick? The second one, okay. So again, on the right side, DC, AD. So on this one, it should be DB and what? DB over DB over Finley, CD, okay? So again, you can go through and kind of figure out literally which sides you're comparing and which triangles you're comparing. But if you have the similarity statement, you can kind of do the same thing that we did with congruence, right? Just sort of match up the vertices and figure out what needs to go in that proportion. Okay, I'm not going to do the next one because I want to make sure we have enough time to talk about some examples. This is literally just kind of explaining what we just talked about, how you can compare the different triangles. This is comparing all 3 triangles here, all 3 triangles here, and all 3 triangles here. And the geometric mean idea is that shows up and H shows up in both of those proportions, opposite corners. Here it's B, here it's A. Now I'm going to kind of jump over that and come down here and look at the 2 theorems that are shown down there. So the first theorem was in a right triangle, drop an altitude, you get 3 similar triangles. The second theorem tells you how sides can be compared. This is a motion that's supposed to help you kind of see what's going on. Boop, 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 boop. Okay, you write the proportion as you are tracing it. So this goes X is to H as H is to Y. Now notice how you have H in the opposite corners, and also notice how we traced H twice. That's getting traced twice, that's why it's showing up twice in the proportion. That means H is the geometric mean of X and Y because it's an opposite corner of the proportion like that. These theorems are super wordy, okay? It's like what in the world is happening? Like, so that's why I'm not really talking about the words there, just trying to kind of show you a way to get the proportions. I call this heartbeat theorem. Do you know why? Diana? Yeah, what does it look like? Bloop, 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 bloop. It's like a heartbeat monitor, right? So that's why I'm calling it heartbeat. It doesn't really matter if you start over here and go over, up, down, and across like that, or if you start on this side and go like that, and that, okay? If we went this way, it'd be y over h equals h over x. You see how you still have the same h in both corners like that, and the cross product would be the same. So because you're getting h squared equals xy, it's going to be the same either way. Now, why is this true? Because you're comparing the similar triangles. You're comparing which 2 triangles? Is that comparing mama and papa, mama and baby, baby and papa? What is being compared there? Liam? Mama and baby, right? So in baby triangle, you're saying short leg to long leg. And then in mama triangle, you're saying short leg to long leg. So this is comparing baby and mama. The motion is just to help you kind of see it easily without having to like think so hard, okay? That is kind of the easier of the two theorems. The other one is not that difficult. It's just the motion's a little bit harder. I'm going to start at the base of the altitude every time. Okay, so I'm going to start down here every time. We can either go left, up, down, and across. Tell me what that proportion is going to be. This, and this. So if I go over, up, down, and across, what is it? Nyla, tell me that proportion. Right, go ahead. Equals B over what? It's me the whole thing. C. Now you can call that X plus Y also. Sometimes you'll have to add those, like if there's a 5 there or something, you'll have to call it X plus Y. Okay, but this one will go X is to B as B is to C. And again, see how the B is the geometric mean in the corners there? That's getting traced twice. That's why it's showing them twice the proportion. Which triangles are being compared there? Which triangles are being compared? Hannah, which triangles are being compared? Baby and Papa, right? Short leg to hypotenuse here, short leg to hypotenuse, and then the other Papa triangle, short leg to hypotenuse. But we're always going to start, this is Baby and Papa. And again, it is short leg to hypotenuse. We're always going to start at the base of the bottom of the altitude. Okay, if I go the other direction, if I go this way instead, tell me what the other side would give you. Finley, can you give me the proportion for if I go this way? Uh-huh. You got to start at the star. So this was X, right? What's this? Yep. Yeah. Y over, that's an A. Yep. Equals C. Good. So Y is to A as A is to C. So that's the same theorem, just like on opposite sides of the triangle. The blue proportion, which triangles are being compared there? Kylie, which triangles are being compared with the blue marks? I mean, like that one is, the pink one is comparing Baby and Papa. What's the blue one comparing? So Mama is long leg and hypotenuse. And then is this in Baby triangle? That's Papa triangle, right? So going that direction, you're just comparing Mama to Papa. Okay, so this one's either Baby and Papa or Mama and Papa. Now, we're going to use those on a few problems here. Oh, and again, on this one, A is the geometric mean between Y and C. A is geometric mean because it's getting traced twice. So it's the hypotenuse, it's also shared, right? Mama triangle has that side and also Papa triangle has that side. Nick? Yes, that's what we're going to do right now. So you'll have like numbers, you'll have X's, you'll have Y's, and you're going to set up proportions to solve for missing parts of the diagram. Now, again, this can only be used when you have a right triangle to begin with and you dropped an altitude to the hypotenuse. It's got to be that situation in order to use this theorem. All right, so here's your triangle's like rotated a little bit. If you want to turn it so it's sitting on a hypotenuse, then it'll be oriented in that way. If you want to take your iPad and turn it, sometimes that helps. So should we do, we've got options. We can either do this, or we can do this, or we can do this. What should the proportion be? Lachlan? Equals what? 4 to 5. Okay, so he's doing x is to 4 as 4 is to 5. Would it be okay to go the other way? Would it be okay to say 5 to 4 and 4 to x? Yeah, how do you know that those are equivalent proportions? How do we know that they're equivalent, Mariana? Yep, you get the same thing, right? 5x equals 16. Oops. X equals 16 over 5. It doesn't matter to me whether you leave it as a fraction or a decimal. Make sure your fractions are simplified. Make sure you don't round. Okay, so decimals that are exact are fine. Just don't round off anything like that. So if it's over a 3 or something like that. Okay, so either way is okay on that one. All right, for the next one. So again, what we're doing is we're comparing baby triangle and mama triangle. So you can always look at them and also just figure out proportions if you want to do it that way. Okay, for the next one. So you want to think all the different options. Now remember, if you do the Nike, oh, I didn't tell you what I call that one. So I call this one Nike swoosh. You have to kind of use your imagination. It kind of looks like a Nike swoosh symbol, or sometimes people think it looks like a boomerang. So you don't have to use those names at all. It's just sometimes easier to say like which theorem you're thinking of. All right, so literally just kind of go, all right, from what I know, what I want to do, this or this or this. What do you think? Emma? Okay, so she's noticing you got 9 here and 3 here, so that's 6, right? And Emma went 3 is to x as x is to 6. Emma, are you right or left-handed? Are you? That's funny because my natural reaction is to go this way. So it's the same. I mean, it's fine. It'll give you the same thing. I just wondered. Okay, so x squared is 18. X is the square root of 18. George, how does that break down? Okay, 3 root 2. You were going to get lots of answers that look like 3 root 2. Okay, there'd be lots of answers with radicals in them. You're never going to round these. You're always going to give them to me in simplified radical form. Okay, so don't go grabbing your calculator and type it in square root 18. I don't want a decimal form of that. I want a simplified radical. Okay, so we know that this is 3 root 2. If you wanted to use that answer you found, sometimes that's helpful, sometimes not. What do you think? Have an idea how to find y? Liam? Okay, you can always do the Pythagorean theorem because these will always be right triangles. You're always going to have 3 right triangles in this particular kind of diagram, right? If you start out with a right triangle, you drop an altitude, you have right triangles. If you want to do the Pythagorean theorem, that's perfectly fine. So it would go 6 squared plus what? Three squared root 2 squared. Yeah, your hypotenuse is y. Now, the reason that I think this is a little risky is because some of us don't know how to square 3 root 2. Sammy, do you know how to square 3 root 2? If I write it like this, does that help at all? If I tell you that you multiply the outside numbers, does that help at all? No. Jackson, can you tell me how to multiply those together? Okay, let me go to somebody else. Caroline. Where is she getting 9 times 2? Moana. Moana. Good. So when you multiply radicals, outside numbers multiply, numbers underneath radicals multiply. So 3 times 3 is 9. Root 2 times root 2 is root 4, which is 2. Another reason that that squared should be 18 is because think about how we got 3 root 2. Since that was the square root of 18, when you square it, you should get 18 back, if it makes sense to you to think of it that way as well. Okay. But this is the hazard of doing it this way, is that some of us are not so great with radicals. So this works. I'm good with that if you can do it correctly, but there might be a way that's easier that doesn't require you to know how to multiply those radicals. Can somebody give me a different proportion? Well, he didn't do a proportion, he did an equation. Finley, what's a proportion that you could use to solve for y? 6 over y equals y over 9. Now, you're going to get the same answer. Now, you'll get y squared is 54. 54 is square root of 9 square root of 6. So you'll get 3 root 6. Now, that's the same thing as you get up here, right? Because that's also 54. When you square root, you're going to get the same answer. But sometimes sometimes you might have to use Pythagorean theorem. Sometimes it's just an option and it may not be the easiest option. But if you're going to use Pythagorean theorem, you got to make sure you know how to square a radical like that. Okay, so this one was using, again, you always start at the bottom there and go over, up, down, and across. 6 is to y as y is to 9.